right, so as we were mentioning before, whoops, there it goes. Eclipsing spectroscopic binaries are good because in that case we don't have to worry about projection effects. We don't have to. Yeah, but it doesn't smell like anything, so I'm going to assume it's just water.
It just passed the smell test.
What's that?
I said it has passed the smell test.
It just passed the smell test. I'm still gonna.
Probably condensation on the coffee board.
What's that?
Condensation on the coffee board.
Yeah, it could be something like that. Yes. Yeah. I mean, I don't think anybody peed on the desk. But
Yeah, that's it. I wouldn't put past those freshmen.
It's. Maybe it was a senior, who knows?
Sometimes you just lose control of your bladder.
Sometimes under the best class, and all of a sudden
We are actually.
Hello, Jacob. Is this all on camera?
I think so. Let's talk about
You still say Gabriel, but I don't think he's taking natural long. He's just taking natural too.
what's the verse of that?
He's watching the videos, just not taking pictures.
All right, anyway, we don't have to worry about the fact that if we know they're eclipsing, then we know they're essentially passing in front of one another. So we know that the orbital plane is very nearly including our line of sight. So we don't have to worry about if there's a tilted orbit where neither star is ever moving straight towards us or straight away from us, so we never see its full orbital speed. This is the definition of the inclination angle. In other words, the dashed line represents the orbital plane sticking into and out of the screen here. And so the inclination is the angle between the orbital plane and the plane of the sky. And so an inclination of 90 degrees is what corresponds to the orbital plane is lined up with us, where we are looking along the orbital plane. And so if there's some other inclination, and here is the well, how convenient, this can be the orbital plane. So there's us looking along, or not the, I'm sorry, this is not the orbital. How convenient, this can be our line of sight, is what I meant to say. If the orbital plane looks like this, well then the best we have is that when the velocity is as close to as possible being straight towards us or straight away from us, as opposed to transverse to us, then the velocity vector would look like that. And so this angle right here would be 90 degrees minus the orbital inclination, since the orbital inclination is, here's the plane of the sky, excuse me, since the orbital inclination is that angle right there, then by the usual arguments, okay, so this is also the orbital inclination, and so that angle right there is 90 degrees minus the inclination. And so the component of the velocity along our line of sight, the radial velocity, the part that the Doppler shift is sensitive to, will be 90 cosine of, will be v cosine of 90 minus I, or in other words, be v times the sine of the inclination. So VR would be V sine I. So the sine of I shows up all the time in discussions in binary systems. The sine of the inclination, for that matter, even of single stars, because if you have a star, the inclination angle is the angle between the rotation axis, like so, or if this is a star, is going to be, get myself turned around. The inclination angle is the angle to the, yeah, to the line of sight. There's the inclination angle. And so if the star is spinning so that we see Doppler broadening of its spectral lines, because part of the star is moving towards us, part of the star is moving away from us, if the inclination angle were 0, we won't see any rotational broadening because every part of the star is moving perpendicular to the line of sight. Whereas if it is tilted perpendicular to us, then we do see the full rotational broadening. Part of the star is moving straight at us, part of the star is moving away from us. And again, it's the sign of the inclination angle that shows up in what fraction of the velocity do we see. And the problem is that with a binary, if it's not eclipsing, we don't have any way of figuring out what I is. There's nothing about the system that tells us what the inclination is if we don't have eclipses. Nothing tells us I unless we have eclipses. Nothing tells us I unless we have eclipses. If we have eclipses, we know that I is reasonably close to 90 degrees. And the farther apart the stars are relative to their diameters, the closer the inclination has to be to 90 degrees in order for there to be eclipses. In other words, in this case right here, if Earth is off in this direction, we would see eclipses here even though the inclination angle is nowhere close to 90 degrees. The borderline case is where you have something like this. If this is the line of sight, if the stars do something like this at some point, that would be where they were just grazing one another as seen from Earth. So if the stars are relatively close to one another, then the inclination angle can be fairly large. And you still, myself straight here, yeah. The inclination angle could be pretty large and still have eclipses. But if the stars are far apart compared to their sizes, notice that the required, that the inclination has to be a lot closer to 90 degrees in that case, right? In other words, here, this borderline case has the inclination angle being very small. So the farther the stars are from one another, the more nearly true it is that the inclination needs to be nearly 90 degrees, basically, in order for there to be eclipses. And you'll do a homework problem where you show exactly what the constraint is. And you'll show that, yeah, for realistic parameters in general, if you see eclipses, you're very close to a 90-degree inclination. And then you'll see that sometimes one star is in front of the other, and you'll have a dimming of the light as a result of that. So that's how we know we've got an eclipsing binary, is that not only do we see the dance of the spectral lines, but we also see periodic dimming as one star passes in front of the other. So let's talk about what we can learn. Stop. In the center of mass frame, so we adopt a frame that rests with the center of mass, but the center of mass is the origin. we have M1R1 equals minus M2R2, right? So in other words, if this is the center of mass, then we know that if we use that as the origin, there's star 1 with mass M1, there's star 2 with mass M2. We know that in that center of mass at the origin frame, that if the position vectors of the two stars are R1 and R2, that M1R1 in magnitude is equal to M2R2, but they're pointing in opposite directions, so M1R1 is minus M2R2. Does that buy into that? Happy with that? And so if we differentiate, that says that M1R1 dot is minus M2R2 dot, where dot means derivative with respect to time. Well, R1 dot is the velocity of star 1. We'll call that V1. R2 dot is the velocity of star 2. We'll call that V2. So this says mass 1 V1 equals minus M2 V2. In other words, they have equal and opposite momenta, right? Because the momentum is mv. And if we take magnitudes, not magnitudes as in brightness, magnitudes as in magnitude of the vectors, then this tells us that just like the distance ratio is the reciprocal of the mass ratio, so too the velocity ratio is the reciprocal of the mass ratio. So V2 over V1 is M1 over M2. So that's true at all times. Since V2 is minus M1 over M2 V1 as a vector, we can see that V1 and V2 point in opposite directions at all times. So if V1 makes an angle theta with the line of sight, then V2 does as well. In other words, if I draw it like this, let's say that's V2, let's say that's V1, let's say it happens to be a case where V1 is the one with the larger magnitude because that star has a smaller mass. Well, here's the line of sight. Then they're both making that same angle theta with the line of sight, just on opposite sides. So they're both reduced by the same projection factor. If we were to measure their Doppler shifts, their radial velocities are reduced compared to their true velocities by that same projection factor. let's say here, in magnitude, because strictly speaking, if it's moving towards us, then we call that a negative radial velocity. If it's moving away from us, we call it a positive radial velocity. Here I'm just interested in how big they are. So M1 over M2 is V2 over V1, but V2 is V2R divided by the cosine of theta. V1 is V1R divided by the cosine of theta. So those cosines of theta just cancel out. So in other words, the radial velocities also have a ratio that is the reciprocal of the mass ratio. So we don't need to know the inclination in order to find the mass ratio of the two stars. We don't need to know I to find the mass ratio. But the problem is that we do need it in order to find the sum of the masses, so that we can actually find the masses of the two stars. What's that?
It was sweet that he was sharing. It sounded like a horror movie instrument.
Oh, yeah. But to find the system mass M1 plus M2, we do need to know I. So for simplicity, we will assume circular orbits. And that's commonly the case for a close binary because as we mentioned earlier when we were studying celestial mechanics, we found that tidal interactions will tend to circularize orbits. So we'll just make that assumption here. For simplicity, we assume circular orbits. This frequently occurs in practice in close binaries due to tidal interactions between the stars. So Kepler's third law says, as we know, put in Newton's form, M1 plus M2 is 4 pi squared over g times the period times h root. So we need to figure out what A is. Well, remember, A is the sum of the A's for the two orbits. In other words, the relative orbit size, its semi-major axis, is the sum of the semi-major axis of the two orbits of the stars around the center of mass. So I can say, but A equals semi-major axis. But these are circular orbits. So that's just the radius of that circular orbit of the relative orbit is given by A is A1 plus A2, and that will just be P over 2 pi, where P is the orbital period, times V1 plus V2. And that's simply because for example, 2 pi A1 will be the circumference of the orbit of star 1, and the circumference is just speed times time. Velocity 1, speed 1 times the period. Speed times period equals circumference for the circular orbit. So A1 plus A2 is just P over 2 pi V1 plus V2. So we can say that M1 plus M2 is equal to P over 2 pi G times V1 plus V2 cubed for our circular orbits here. Just plugging in then for A cubed over there. A cubed would be, no, it's the P cubed, wouldn't it? Yeah, this was P cubed, right? Oh no, because I divided it by a P over there, so what did I do here? I think I should have a P squared over there. Yeah, I think I just, yeah, I should have a P squared. I never noticed in my notes, or probably did notice in my notes, I should fix this, and then never fixed it later. So yeah, P squared over 2 pi G times V1 plus V2 cubed. So, if we look at what the radial velocity curve would look like, here, if you have circular orbits, you're going to get sinusoidal radial velocity curves, because remember that uniform circular motion, if you project it along either axis, that's sinusoidal. So in other words, if I look at the component of the velocity along the line of sight, let's say that's the orbit of one of the stars. Let's say Earth is off along the x-axis here. Then the velocity component along the line of sight is just the x component of the velocity. But if I look at uniform circular motion, we find that either component, the x or the y component, is sinusoidal in uniform circular motion. Do you remember that result? Can I just state that result? So therefore, the radial velocity curve, if you plot what you measure for the line of sight velocity as a function of time, you'll just get sinusoids. And if the orbital plane contains the line of sight, then the amplitudes of those sinusoids will be the actual orbital speeds of the stars, because there will be moments when the stars are moving straight away and straight towards us. And so the maximum radial velocity is in fact the true orbital velocity in that case. So I'll just state for circular orbits, we get sinusoidal and their amplitudes are the true orbital speeds. Since there are times when the stars are moving straight towards or straight away from us. So we see the full orbital speed at those moments in the Doppler shift. If I isn't 90 degrees, if there's some inclination there, well then the maximum velocities are reduced by that factor of sine I. The maximum radial velocities and thus the amplitudes are reduced by a factor of sine I, by the inclination. So if we don't know I, we can't find the true size of the orbit. So we can't find M1 plus M2. Brace down. But if it's an eclipsing binary, we can assume that the amplitudes of the radial velocity curves are telling us V1 and V2. And then we have everything we need, because now we've got the sum of the masses. The ratio of the amplitudes gives us the ratio of the masses. And then we've got two equations and our two unknowns. We know the sum, we know the ratio. That allows us to determine the two masses individually. Okay. Any questions? And of course, there will be a problem where you get to do that. Here's the parameters of this eclipsing binary. Two stars have such and such an orbital period, and the radial velocity amplitudes are this and that. Determine the masses of the two stars. And you've got all the tools you need to do so. Okay, any questions? All right, so it still is interesting to explore what happens if you don't know the inclination. What constraints can we put on the system if we don't know the inclination? Because, for example, when we're trying to determine if there's a black hole in some binary system, well, we don't get any spectral lines from the black hole, but we might see the dance of the spectral lines for a normal companion that is in orbit with the black hole. And one of the ways that we try to determine if some unseen companion is a black hole versus a neutron star versus a white dwarf is to try to put some kind of lower limit on what the mass of the unseen companion, the compact object that might be a neutron star but might be a black hole, is. And if you could say, well, it's got a mass of at least 4 times the mass of the sun, you can know that it's not a neutron star. You can know that it has to essentially be a black hole. Now we have lots of, at one point, this was like trying to resolve the question of, do black holes exist? We're past that now. We have lots of evidence for the existence of black holes, including gravitational waves from galaxies billions of light years away that are only reasonably explained as black hole mergers for things that have dozens of times the mass of the sun. So it's no longer so much an issue of, do black holes exist? But on the other hand, it still can be an issue of, in this system, is that a black hole or is it a neutron star? So it's still of interest to talk about what kind of constraints we can put here. Furthermore, with planets that we detect via Doppler shifts of their star, we're in exactly the same situation. It's like having a star system where you can only see one set of spectral lines shifting back and forth. What kind of limits can we put on the mass of the unseen companion based on that? So this involves what we call the mass function. Amplitudes of the radial velocity curves are V1r is equal to V1 sine I. I've got it flipped in my notes, so I've got it over sine I, but no, it's times sine I. It's smaller than the actual radial velocity, so I need to fix that. V2r is equal to V2 sine I. So our m1 plus m2 is really p squared over 2 pi g times, let's see, where am I? Where is this from here? So it'll be, you sure I have this right here? Yeah, so it'll be v1r plus v2r cubed divided by sine cubed I, since V is V1R over sine I. V1 is V1R over sine I. V2 is V2R over sine I. So I plug them as the radial velocities over sine I here, and then I cube it, so I get a sine cubed I down in the denominator. But V2 is M1 over M2 V1. And actually I could say V2R is M1 over M2 V1R. The radial velocities are also in reciprocal of the ratio. The ratio of the radial velocities is the reciprocal of the mass ratio. So we can rewrite this as m1 plus m2 is equal to p squared over 2 pi g times, well, I was really convinced it was p when I wrote these notes. Why? It is p squared, right? That's what
Yes.
Yeah, it is p squared at some point. P squared over 2 pi g times, I gotta look at that carefully just to be sure, but yeah, okay. I'll stay convinced too because I haven't looked at it, but yeah, it just seems like it should be. P squared over 2 pi g times V1 radial cubed over sine cubed I times 1 plus m1 over m2 cubed. So in other words, I just put in V2R was m1 over m2 V1R, right there. And the p squared over 2 pi g times v1r cubed over sine cubed I times, I'll just factor out a 1 over m2 cubed times m1 plus m2 cubed. I just write the 1 plus m1 over m2 cubed as m1 plus m2 cubed over m2 cubed. Cubed is what I meant here. So that m2 cubed over m1 plus m2 squared is equal to, I gotta check that because again, I just keep writing p, I had p in my notes over and over again. So, does everybody think it should be p squared? Have we really checked that? You know what I mean, like from back earlier?
Yeah, I thought it.
Yeah, but I'm just, apparently when I wrote these notes, I was so convinced, and I don't remember in prior years going through and saying, oh man, it should be p squared, oh man, it should be p squared. So, it was, we were saying m1 plus m2 was 4 pi squared. Oh, it's GP, yeah, it's GP squared A cubed, right? So, yeah, and then, oh, it's GP squared A cubed. Yeah, see, I think I wrote GP last time.
Yeah.
So, so there is only one P hanging around. So, okay, so I was right. I think I wrote this wrong before, and nobody caught that. So, okay, all those P squared subsequent do in fact just say P's. Fifth. Okay. Good to have that forever on the video. Yeah. Alright, so this relationship makes a box around it. So notice that it only contains one radial velocity in it, namely star 1. So in other words, and whichever one we can see could be star 1. So in other words, you only need observations of the amplitude of one radial velocity curve. You don't even have to see the second star in order to figure out the right-hand side of this. You just need the amplitude of the radial velocity curve for one star, and the orbital period just comes from how long does it take for one cycle of the radial velocity curve. And you know what g is, and you know what 2 is, and you know what pi is, so we're good to go on the right-hand star from observation, from the right-hand side from observation of one star. So let's talk about why this is actually useful. This expression is useful if we do not know I, or if we can only observe the spectrum of one of the two stars. side, the LHS, is what we call the mass function. While the right-hand side depends on readily observed quantities for one star only. So again, we could be talking about a binary star system where one of the companions is a potential black hole candidate, or one of the companions is a planet, so that we're only seeing spectral lines from the star. And the point here is that the mass function provides a lower limit on M2. In other words, a lower limit on the mass of the thing we don't see, the black hole candidate, or the planet, or whatever. Because it is always less than M2. It's always less than M2. That thing on the left-hand side is always less than M2. Now I left out this. Okay. We left out the sine cubed I on that side. Pit. Okay. Okay, we have to start over so the video's right. So, okay, I'm just going to go back to the start of class. There's a sine cubed I there that we forgot to put there from the prior line. So why is the left-hand side always less than M2? Why? Because sine cubed I is certainly less than or equal to 1. I maxes, sine of an angle maxes out at 1, so if you cube it, you are 1 or smaller. And m2 cubed divided by m1 plus m2, the quantity squared, is equal to m2 times the quantity m2 over m1 plus m2, the quantity squared. Right? In other words, we've got m2 cubed over m1 plus m2 squared. We'll just factor out an m2 and write it as m2 times the quantity m2 over m1 plus m2 squared. And the term in parentheses is strictly less than 1, right? m2 divided by something plus m2 has to be less than 1. Parentheses is less than 1. So the point then is computing p over 2 pi g times v1r cubed, the amplitude of the radial velocity for the visible companion, computing that quantity gives us the smallest value that the mass of the mass of the unseen gives us a lower limit on the mass of the unseen companion. We know that its mass is at least as big as this, and in fact probably greater. So it's not what we would like. We would like to know what M1 and M2 actually were. But on the other hand, if our job is figure out if that unseen planet is potentially Earth-like, and you calculate the mass, and you calculate using the spectral lines of the star, the quantity there on the right-hand side, and the answer comes up that the mass of the planet is at least 15 times the mass of Earth, you can conclude confidently that that is not a terrestrial planet. What if you compute it and you find the mass of the planet is at least the mass of Earth? Would that allow you to conclude that it was a terrestrial planet? No, because knowing it's at least the mass of Earth means it might be a terrestrial planet, but it might be 20 times the mass of Earth, right? So it's a lower limit. So in other words, it's better at excluding possibilities than it is of proving that it's a certain type of thing. On the other hand, in a binary star system with an unseen companion, we think the maximum mass that a neutron star can have, kind of the next step before black holes, is at most around 3 times the mass of the sun, probably a bit less than that. If the mass function turns out to be 9 times the mass of the sun, that ain't a neutron star, and so in that case, the reasonable candidate is that it's a black hole. So, in other words, if you're trying to show something might be something that has a low mass, this won't tell you for sure. It can tell you, well, you're consistent with that. But on the other hand, it might not be. But if you're trying to show that it's something that has a relatively high mass, then this can definitely be your friend. You can show, well, it can't be this other thing that would have a lower mass. Okay? Any questions? Let's take a break, shall we? And hope that the second period isn't one more. Man, I wish I could just retape the whole, or re-video the whole thing. I have to put a disclaimer in this one on like the little notes.